very good afternoon to everyone. A warm welcome to all the participants friends to the day 10 of 8 training and mock test organized by Department of Civil Engineering, VVC, Mysuru. Today, for the second session, we have with us Dr. VVC, Mysuru, who is going to help us in cracking gate problems on foundation system. I welcome Dr. Sk Prasad sir to the session. Welcome you, sir. So let
Thank you, Professor Kanmani.
Thank you, sir. So let me introduce Dr. Sk Prasad sir to the gathering. Dr. Sk Prasad sir has a vast experience of 35 years in teaching and research. He worked in SJC Mysuru for 32 years, and now currently he is heading the Department of Civil Engineering in VVC Mysuru. He did his BE from University of Mysore, securing first rank and obtained 4 gold medals in 1982. He also obtained his master degree from IIT Kanpur in 1985 and doctoral degree from University of Tokyo, Japan in 1996. He has also been the visiting professor for Asian Institute of Technology, Thailand, and he also served as professor in MSRIT Bangalore for 3 years. He has over 175 technical papers in national and international journal and conferences. He has guided more than 70 master projects and 3 PhD students. Presently, he has 3 more PhD students who is working under his guidance. He has completed many sponsored projects from AICTE, DST, and JSSMFU. He's also serving as the National Executive Council member of Indian Geotechnical Society. With this brief introduction, I once again welcome Dr. Sk Prasad sir, and I hand over the session to you to listen to Dr. Sk Prasad sir. Over to you, sir.
Thank you. Thank you, Professor Kanmani. Thank you for your elaborate, description of me. It was a pleasure listening to you. And friends, this is the fourth time I'm speaking to you all on the training program related to foundation engineering. So we have covered, important topics of foundation, and I presume, today and perhaps in the next class, I'll be talking about rest of the topics in foundation engineering. And it's always a pleasure to share some of the experiences, and hence, without wasting much time, I go on to the slides. Madam, is the slide visible?
It's clearly visible. It's clearly
Okay,
visible, sir.
all right then. Okay, friends, let me go on to the topic of retaining walls, basically topic of earth pressure. I just want to show you some of the retaining walls before going on to the theoretical aspect. Please note that, these are the two roads at two different elevations. Naturally, there is earth here, and this earth has to be supported, and hence you have a wall here. Why should it be supported? Earth is particulate in nature, therefore it cannot stand by itself. So, if you leave it like that, it's going to fall down. To stop it from falling, you need a wall here. And hence, this retaining wall has retained earth at two different levels. On one side, earth up to here, on the other side, up to the other place. Likewise, you can see many retaining walls. See, this one is a hilly terrain in which you would like to have a road excavated, and naturally this excavation is made, and it is a vertical excavation. You can't expect it to stand by itself, so it's going to fall down. To stop it from falling down, you're going to have a retaining wall here. This is another situation where you want to have a retaining wall. You have a tall, multi-storied building. Naturally, you'll have many floors below the ground also. Specifically for the purpose of car parking, we will have underground cellar, level 1, level 2, like this. So if I take an external wall here, something like what you see here, okay, yeah, something like what you see here, this wall is retaining earth up to this level here, and on the other side, it is empty, so it is space for car parking. So earth is there up to here, and if this wall is removed, this earth portion will fall down. Plenty of occasions. This is a retaining wall built out of sheet metal, it's sheet pile. So what is it doing? You are retaining earth at two different levels. Of course, you also have water here, and majority of the hydraulic structures, we are going to think of not the conventional retaining walls. So metal wall, sheet walls, sheet piles. Well, here, this one is in Indian Institute of Science, entrance to the, subway, and on top here is the national highway going towards Mumbai at Bangalore. Okay, and you can see this entire thing is a retaining wall. It is retaining earth up to almost this level on the other side, and it is open on this side. Plenty of such retaining walls. I just would like you people to see. I only wanted you to have a feel of where all retaining walls are built. This is a retaining wall. You can see here, there is some structure, and hence, there is soil up to here. Okay, soil up to here. This one also is a retaining wall. Soil up to here on that side, soil up to a lower level here. This is the height of the retaining wall. Can you see this? Again, this is a retaining wall. You remove this wall, soil from here falls down. In other words, I just want to tell you at this point of time that the wall is being pushed by the soil, or soil is exerting a pressure on the wall. If you want to design this wall, you should know what is the amount of pressure the wall is going to put onto the soil is going to put onto the wall, and that depends on several factors related to wall itself, maybe the height of the wall, maybe the surface roughness, whether the wall is vertical or inclined. It also depends upon the backfill soil. The soil behind the wall is called backfill soil, its properties. So whether the backfill soil is horizontal or is it inclined, is it in the form of layers, is there water table, is it a cohesive soil or granular soil, several factors. Based on this, you should find out the lateral earth pressure, and it's a very important quantity, important measurement for the design of retaining walls. So here are some occasions again, where retaining walls are built. This one is an embankment, okay, with the top surface here and side slope, maybe one vertical to two horizontal, pretty flat, and on top of it, Shinkansen bullet train was being built, and was built sometime in 1960s, 70s. Due to the growth of population, growth in cities, they wanted to increase the number of tracks for bullet train, and they thought about extending this width of the top. But then there is a lot of urban area here, and that they did not want to disturb. So instead of an embankment with a gradual gentle slope, it was decided to have a wall built here and fill up this entire portion. So that is a retaining wall. It is going to retain earth at higher level on this side, lower level on the other side, and this higher level earth, in addition to the surcharge load, which may be even dynamic due to the movement of Shinkansen or bullet train, will cause earth pressure onto the wall. So the wall should be designed to take care of this earth pressure. Again, some more occasions where retaining walls become essential. These are all the situations. Well, this is a harbor facility. We call this a ski wall many a times, QUAY wall. This is sea, and this ski wall is subjected to lot of horizontal earth pressure on this side. There is also water pressure on the other side, and this is the including the wave pressure due to the sea waves. All of you are familiar with this figure. So this talks about the Palm Island in this shows Palm Island in the city of Dubai, and Palm Island is built into the sea, and all around there is a retaining wall. So it is retaining earth, okay, on one side, and water, sea water on the other side. Some more pictures of retaining wall. Even in a swimming pool, when you want to build a swimming pool, all sides, okay, you will have wall. So one side it retains earth, on the other side, when swimming pool is full, it retains water, and when it is empty, there will be no pressure, there will be only pressure from the soil side. So I just thought that you people should have an idea about the applications. And one of the very important things you need to determine here is the earth pressure. And this earth pressure, you need to compute the magnitude of earth pressure, the resultant of the earth pressure, the location of the resultant, and so on. For that, you have a number of theories. Two very important concepts are given by, Rankine and Coulomb. So we will look into Rankine's theory as well as Coulomb's theory with regard to earth pressure, and try to solve a number of problems which are familiar ones for gate examination. So Coulomb was in the 18th century, 1736 to 1806. He built his theory of earth pressure way back in 1776. Please note, at that time, geotechnical engineering had not developed. So he developed most of his theory through intuition. So did Rankine. Almost, about 70 years, 80 years later, Rankine in 1857 built his theory for the earth pressure. So we do use Rankine theory more often, but Coulomb's theory is equally prominent. Okay. Naturally, whenever you think of any theory, you need to have the guidelines on which the theory is developed. So you need to assume certain things, because the system may not be perfect, and especially in case of soils, you don't expect everything to be perfect. So let us see the assumptions he made before making up his theory. And some of these assumptions are common for all analysis which we do. And already I have dealt with and shown you that soil is one of the most complex construction materials, and not easy to handle, not easy to consider the reality there. So one of the important assumptions which are made is, soil is isotropic and homogeneous, which is never the case. So the properties are same at each and every place, properties are same in every direction. Soil is cohesionless. All of you know that soil exists in different varieties. One extreme is, cohesionless soils, those having only friction angle, granular soils. The other extreme is purely cohesive soil. The soil doesn't possess any friction angle. Every strength aspect is through the cohesion which the soil material has. So in this case, it is assumed that soil is cohesionless, and then we make modifications and apply it to the other type, cohesive type of soils also. The backfill surface is planar, which may be inclined or horizontal. Please note, friends, this is the wall, this is the backfill side, this is the soil side. Soil extends up to this depth, this level on the right side, whereas it extends up to this level on the left side, and this is the height of the wall. So in this backfill portion, the surface is either horizontal or inclined, but it is plane. It is planar. The rupture surface plane is a plane surface. The rupture surface is a plane surface. So, when the load is applied, wall moves away from the backfill in many cases. It moves towards the backfill also in certain cases. And whenever the wall moves, there will be a failure surface which is created. And it is assumed that the failure surface is also planar. Failure wedge is a rigid body. So a portion of the soil moves with the wall, either away or towards. And when a portion of the soil moves with the wall, it is considered to be simply part of the wall, and hence that entire triangular portion is considered to be rigid. It doesn't experience any deformation. That's the assumption which is made. The back of the wall is smooth, so that lateral earth pressure acts parallel to the ground surface. back of the wall can never be perfectly smooth. Still, it is assumed that it is smooth. Therefore, there is no friction between the wall and the soil backfill portion. Therefore, entire pressure is assumed to be horizontal. Failure is a plane strain unit problem. Unit interior slice from an infinitely long wall. So please note that most of the problems we try to solve it as two-dimensional problem. Two-dimensional because it becomes very complex to consider it in three dimensions. And when we make it in two dimensions, the best possible assumption in geotechnical engineering is plane strain whenever the length of the structure is going to be large. So here, length of the retaining wall perpendicular to the slide is considerable compared to the other two dimensions. So we assume it to be plane strain problem, and hence strain in that direction perpendicular to the slide is considered to be negligible. So most of the strain is considered to be acting in the other two planes. Friends, all of us need also to be familiar with more Coulomb failure criteria. Whenever the soil fails, one of the very important theories which we use is more Coulomb failure criteria in case of soil. I have told you that soil is particulate in nature, therefore its failure is different from that of other metals. And its failure is not just heralded by the particle movements. Even the confinement plays an important role. Therefore, you just walk on the beach surface. When you put your feet on the sand, your feet are likely to go down a bit, indicating that at the surface, sand is very soft. Same thing doesn't hold good maybe 1 meter below, 10 meters below. Soil will be very stiff. It will not move easily. That is because of the confinement. So, confinement plays an important role in the failure of the particulate materials like soil. So, Moore Coulomb failure criteria is one very popular theory which is used, which uses two parameters to define strength of the soil. One is C cohesion, another is phi friction angle. So cohesion is derived in the cohesive soils, like clay soils, which is mainly due to the adhesion between the particles. Okay, particles of same type, we call it as cohesion. So between the particles, whatever the sticky nature is there, that is cohesion. And then you have the friction angle, which is mainly due to the friction developed in granular material. And each particle is having different size, shape, and when it has a friction between the other particle, contact between the other particle, there will be friction generated, causing resistance to movement, which is given by the friction angle. And we have tau equal to C plus sigma tan phi, which is a standard equation for Morse Coulomb criteria, where tau is the shear strength, C is cohesion, sigma is the confining pressure, and phi is the angle of internal friction. And whenever the stress is equal to tau, that is shear strength, the material has just been on the verge of failure. And if the shear stress is much lower than the strength, you say that the material is in safe position. So if you take any element of soil, so it has the vertical component and horizontal components of normal stresses. When it is, having level ground and no unsymmetry and so on, there will be only the normal stresses which are acting. One is vertical and another is horizontal. Majority of the times, vertical stress is higher compared to the horizontal stress. Soil not being, isotropic. Whereas in case of water, these two are equal at any depth. But in soil, they are different. Majority of the times, vertical stress is higher than the horizontal stress. So vertical stress, we call it sigma 1, major principal stress. Horizontal stress, sigma 3, minor principal stress. And we can, using more Coulomb's criteria, we can bring in a relationship between these, and sigma 1 equal to sigma 3 tan squared alpha plus 2c tan alpha is a standard equation representing more Coulomb criteria, where alpha happens to be 45 plus 5 by 2. So this is a familiar thing which we commonly utilize in earth pressure theory. We should understand three extreme situations, two extreme situations: active state, passive state, and a situation which is normally existing at rest state. So three situations for the lateral earth pressure should be the thing of remembrance for everybody. So whenever there is at rest situation, okay, under normal circumstance, you use at rest state, and two other extreme states when the failure can happen are active state and then passive state. So please note that this is the wall, this is the height of the wall. On one side, you have soil up to the full. This is called backfill. On the other side, soil is only up to here. If the situation is that there is no strain developed in the backfill portion, there is absolutely no strain developed in the backfill portion, the situation is called at rest situation. So at rest situation also, you will see that soil will exert some pressure on the wall. If you remove the wall, soil will fall down. But soil is under no strain situation. On the other hand, one extreme situation is this soil exerts a pressure which the wall cannot take. So wall is likely to fall down. Wall is going to fall, away from the backfill. So that is due to the pressure exerted by the backfill. So, under this pressure, soil is likely to experience a failure, which we call as active earth pressure case. All this is because of the weight of the soil, weight of the backfill, which is pushing the wall. And hence, under this situation, the vertical stress will be higher than the horizontal stress, which we call as sigma 1 major principal stress, and the horizontal one is minor principal stress. In this case, wall is always likely to move away from the backfill. You have the third situation wherein wall itself is pushing the soil due to some external force, due to some situation. Wall itself may push the soil. Maybe one of the cases I will try to show how things will be when the wall pushes the soil. So at one particular point, soil will fail. If you consider any element here, it is the push from the wall which is mainly significant, and hence that causes major principal stress. Whereas the weight itself, is a smaller quantity that can causes minor principal stress. In this case, wall moves towards the backfill, and it experiences a deformation. It experiences a movement, okay, in the backfill region, backfill uh, zone. So very clearly, you have three types of earth pressures, and I have just plotted the earth pressure, lateral pressure, okay, in the vertical axis, and then strain along the horizontal axis. When there is no strain, whatever earth pressure you see, we call it as at rest earth pressure. But whenever the soil pushes the wall away from the backfill, which is a common situation of failure, you'll have sufficient amount of strain the soil will experience, and it is the gravity loading, it is the vertical loading which is responsible for the soil, backfill soil, to push the wall, and hence you have active situation. That is when the movement is away from the fill. On the other hand, when you allow for movement towards the fill, you need to apply an enormous amount of pressure onto the wall. So wall has to push the backfill and make it fail. So that will be called passive situation. And in this case, movement is towards the fill. So please note that whenever movement is towards the fill, the amount of strain experienced is not so much. Okay, amount of strain experience is not so much. Whereas whenever it is the active situation, we will have considerable amount of movement. So let me first take you on to active earth pressure situation. And basically the objective is you need to find out how much is the pressure at different depths below the ground level in the retaining wall. You also need to find out perhaps the total thrust, and you need to know the location at which the total thrust acts. So these are all the requirements from the point of view of determining the earth pressure. So let me take the first situation where I have a wall of height h being built to hold the backfill soil on one side and the other side is free. This is the active situation in which wall is likely to move away from the backfill. That is because the push backfill is going to exert. As I mentioned, if I take any element of soil here, mainly the vertical gravity force is responsible for the push, and that is the one which has the major magnitude. Hence, we call it as sigma 1 equal to major principal stress. On the other hand, the lateral pressure which is exerted is sigma 3. And our job is to find out this lateral pressure from the top to the bottom, the distribution of the lateral pressure from the top to the bottom, and hence, of course, to find the total earth pressure. So please note that the vertical stress in this case is higher than the horizontal thrust. So this is for the situation of active earth pressure. You must be familiar with this equation, sigma 1 equal to sigma 3 tan squared alpha plus 2c tan alpha. How did we arrive at? We arrived at from the Mohr Coulomb criteria, and this derivation is a very simple derivation of satisfying the equilibrium. And if you consider cohesion-less soil, C is 0, then sigma 1 is equal to sigma 3 tan squared alpha. Under active situation, you should always know that sigma 1 is the vertical stress, sigma 3 is the lateral pressure. That's what you need to determine. So let me go over here. So please note that sigma 1 is the vertical stress, which is equal to, at any depth, gamma times z, where z is the depth, gamma is the unit weight of soil, assuming the soil to be isotropic having same unit weight. Sigma 3 is the horizontal stress exerted, which is the lateral earth pressure, that's equal to Pa, and alpha is equal to 45 plus 5 by 2. So C is equal to 0 in this case. So substituting, sigma 1 is equal to gamma z and sigma 3 is Pa. So gamma z is equal to Pa tan squared alpha plus 0, or what we want is Pa, that is gamma z by tan squared alpha, or gamma z into cot squared alpha. From here afterwards, this value cot squared alpha, which is simply a function of phi, we'll call it as Ka, where Ka is called the coefficient of active earth pressure. So lateral earth pressure Pa at any depth is equal to Ka times gamma z. K is a function of phi, gamma is the unit weight of soil, and Z is any depth. At depth Z equal to 0, that is top surface, Pa is 0, and at the bottom, Pa will be maximum. The variation is linear. So Pa is equal to Ka gamma Z. I want you people to remember. Here Ka, this is easy to remember, is 1 minus sine phi by 1 plus sine phi. Normally the value of Ka is less than or at the most equal to 1. Therefore, numerator is 1 minus sine phi, denominator is 1 plus sine phi. Imagine when phi is equal to 0. When will it happen? Maybe soil is like a fluid. Okay. Then Ka will be equal to 1. Imagine when phi has some value, say 30 degrees. Then sine phi is equal to 0.5. Therefore, 1 minus 0.5 by 1 plus 0.5, that's equal to 1 by 3. So Ka generally lies between 0 and 1. And Pa is equal to Ka, the coefficient, into gamma into Z. As I told earlier, there are many factors on which the active earth pressure or in general earth pressure depends. So we shall consider each of the factor differently. So the first study can be with a homogeneous backfill. Then we can go to the layered backfill, and then a backfill with a surcharge. We can consider inclined backfill, inclined wall, and finally we also can consider cohesive soil. So we'll go one by one. So one is homogeneous backfill. That means the entire backfill has uniform soil properties. So in that case, already PA is equal to, that is earth pressure, PA is equal to K times gamma Z. At Z is equal to 0. Okay, at Z is equal to 0, that is top of the fill. PA is 0. And at Z is equal to H. PA is equal to K times gamma H. The variation is linear from 0 to here, linear. Therefore, the resultant total pressure is supposed to be acting at a depth h by 3 from the base or 2h by 3 from the top. What is the magnitude? It is equal to area of this triangle, that is half into Ka into gamma into h squared. So that is the push which the soil backfill is exerting on the wall, and the wall has to be designed to withstand that push, withstand that force. So that's what I said. Pa is equal to Ka gamma h squared by 2, acting at a height of h by 3 from the base. Then, if there is a surcharge on top, please note that there can be surcharge due to some new structure which is built. Let us assume that the surcharge is of uniform pressure Q. And if that is the case, then please note that the lateral earth pressure, as I told in the previous case, holds good. Plus, there is an additional effect of surcharge. We need to consider both of them. So, if you take surcharge into account, so if Q is the surcharge, then surcharge is going to have a uniform pressure throughout equal to Ka times Q, where Ka happens to be the coefficient of active earth pressure, which is equal to 1 minus sine phi by 1 plus sine phi, plus the earth pressure developed due to the backfills property. At depth Z is equal to 0, the earth pressure is 0, and at any depth, it is Ka times gamma H. So you need to consider Ka into Q, which acts throughout uniformly, plus Ka gamma H to 0, which has a linear variation. And if you want to find the total active earth pressure, please note that you have the triangular portion plus the rectangular portion combined together. You need to take the resultant thrust considering these two forces. So you can consider the area of the trapezium and arrive at. Therefore, the height at which the resultant is acting is not h by 3, is not h by 2. It is somewhere in between these two. H by 3 for this triangular variation, h by 2 for this surcharge variation. So it is in between h by 2 and h by 3. Then let us consider a situation where there is groundwater table. I always keep mentioning that water is the worst enemy to a geotechnical engineer. It can cause a lot of problem. So in this case also, the presence of water can possibly increase the earth pressure. So let us try to see that. And groundwater table may exist at the top of the backfill or at some depth below, inside the backfill portion, or maybe even at a deeper elevation. If it is at a deeper elevation, we don't have to take its effect into consideration. But if it is anywhere from the top till the bottom of the wall, we need to take the effect of the groundwater table. Let us assume that groundwater table is anywhere from the top to this one. So in this case, Pa is equal to Ka gamma submerged into Z plus gamma W into Z. I want you to very clearly understand. Soil is in submerged state. That is because of the presence of water. And then the water itself will be exerting a horizontal push. The push exerted by water, if you take separately, it is gamma W times Z. On the other hand, the soil's pressure has to be the effective value. So you need to consider gamma submerged into Ka, which is the coefficient of active earth pressure into Z. So Pa in this case will be equal to Ka gamma submerged into Z plus gamma W into Z. At Z is equal to 0, both of them will be 0. At Z is equal to H, it is equal to Ka gamma submerged into H plus gamma W into H. Please note that gamma W is approximately 10 kilonewton per meter cube, 9.81 kilonewton per meter cube. Gamma submerged is equal to gamma saturated minus gamma W. Okay. So your earth pressure diagram will be something like this. It will be triangular. One portion is for water, another portion is the soil in the submerged state. Ka gamma W in gamma submerged into H and then gamma W into H. Let us consider a situation where you have a sloping backfill. Generally, in a hilly terrain, when you build a retaining wall, this is the aspect which has to be considered. Many a times, I have noticed in the design, people forget to consider the sloping backfill. But it's going to be very critical, very dangerous if we don't consider this effect. The earth pressure values may be 2 times more, 3 times more. We just cannot imagine. So, if you have a backfill which is sloping, as in case of a sloping ground in a hilly terrain, the angle of slope can be considered as beta, and this beta is equal to 0 in level ground, and it increases when you have a steep sloping ground. And let me consider again the cohesionless soil. Then the equation for Ka is going to be as shown here. Please note here. Here, the equation, the trigonometric equation which you see is a function of both phi and beta. Phi is the angle of internal friction and beta is the slope angle. So Ka is found to be equal to cos beta into, in the numerator, cos beta minus root of cos squared beta minus cos squared phi, and in the denominator cos beta plus root of cos squared beta minus cos squared phi. So based on this, you find out Ka, and the active earth pressure is going to be Ka gamma H at H is equal to 0, or at the top, its value will be 0, and at the bottom, it is K times gamma into H. K is what I already explained, and in this case, the total pressure Pa is equal to Ka gamma H squared by 2, and you should know that the total pressure is also inclined to the wall at an angle beta, which is the angle of inclination of the backfill. So this is how the distribution of the active earth pressure is going to be in case of a backfill which is inclined. You may have a situation when the wall is not vertical. Wall may be also inclined. Most of the times you have the top surface of lesser cross section compared to the bottom surface, and what I have shown here is the typical situation. What do? In this case, you just assume that this entire portion is filled with some material. It could be soil itself. So you consider the vertical portion here. For that, you can have the earth pressure drawn, earth pressure determined. And this triangular portion is the weight of the soil here. And consider that, and hence find out W. Resultant active earth pressure will be considering the combinations of, you know, the weight of the triangular portion and the backfill when it is vertical exerting the pressure. So here alpha is the inclination of the wall with vertical, W is the weight of the backfill in triangular portion, and PA1 is the active earth pressure. Let us move over to the situation when the soil is cohesive. I told you whenever Rankine generated his theory, he assumed that the soil is cohesionless. Now we are applying the modification. So what is that we are doing? Already you know that sigma 1 equal to sigma 3 trans squared alpha plus 2c tan alpha is based on the Moore Coulomb criteria for major and minor principal stress relationships, and this equation is familiar. We had assumed c equal to 0 and only considered the two sigma 1, sigma 3 and alpha, which is equal to 45 plus 5 by 2. In this case, we'll consider c also. So then what happens? Sigma 1 is equal to gamma times z, that is the vertical stress. So at z is equal to 0, it is 0. And when you go deeper, it increases linearly. Sigma 3 is the lateral earth pressure which we are computing, which we are using. That is PA tan squared alpha plus 2c tan alpha. But what we need is the active earth pressure PA. When C was 0, we had just taken it as gamma z by tan squared alpha or gamma z cos squared alpha. But in this case, we have this cohesion term also to be taken into account. Therefore, PA is equal to gamma z cot squared alpha minus 2c cot alpha. And this is the relation which we have to remember whenever we deal with cohesive soils. So what does it mean? There is this negative term. So cohesion will reduce the earth pressure. So it will actually provide some kind of tension to the soil. It can take some amount of tension. Cohesion actually reduce the earth pressure. By what quantity? Equal to minus 2c cot alpha, where alpha is equal to 45 plus 5 by 2. So PA is equal to cot squared alpha is nothing but Ka. Ka is coefficient of active earth pressure. That's equal to 1 minus sin phi by 1 plus sin phi. Therefore, you have Ka gamma z minus 2c times cot alpha is root of Ka. So Pa is equal to Ka gamma z minus 2c times root of Ka. So please note, friends, the relation when you have a cohesive backfill. I'll again tell you, this is the equation which you have to take. So what happens at z is equal to 0? At z is equal to 0, Pa will be equal to negative. That means it can take some amount of tension equal to 2c times root of Ka. That's what I have written here, minus. And this entire earth pressure in this diagram is on the negative side, it can take. And then when you go to the depth equal to h, it is equal to z is substituted by h. It is k times gamma h minus 2c into root of Ka. And hence, this is the earth pressure diagram. And what is this depth at which earth pressure will be 0? I have called it as z naught. So for that, you need to take this equation. Earth pressure is 0. So put Pa equal to 0 and Ka gamma z naught minus 2c root Ka equal to 0, or z naught is equal to, you get the equation 2c root of Kp by gamma, root 2c root of Kp by gamma. So this entire triangular portion, top triangular portion is negative. That means, soil has the capacity to withstand the pressure. It can stand by itself. So where the this negative portion can be compensated in the positive side here, and this is the height hc, which we call as critical depth, up to which clay soil can stand by itself without giving any additional support, and that is equal to 2 times z naught, so that the earth pressure here is 0, and 2 times z naught is simply 4 times c into root of Kp by gamma, which I want you people to remember. So earth pressure distribution will be something like this, and these are common questions in gate. Majority of the gate problems have cohesion also in addition. So friends, so far I have talked on active earth pressure case. That is when the wall is being pushed away from the backfill. That's because the backfill is going to push the wall. You have another situation in which wall itself moves towards the backfill and hence causes the failure of the backfill. You have the third situation where wall does not move either to the left or to the right, either towards the backfill or away from the backfill. That situation is when there is no strain, that is earth pressure at rest. So going forward, let us try to consider passive earth pressure situation. That is when the wall is likely to move towards the backfill. Somebody is pushing the wall, and hence backfill is going to be pushed. That situation we call as passive earth pressure. Here also we need to find out the intensity of passive earth pressure from the top of the wall till the bottom. We need to find out the total pressure, total thrust. We also need to find out the location at which the pressure acts. Okay, and we do the same thing like before, considering a simple situation of homogeneous isotropic backfill with a horizontal surface. Two, slowly we keep on adding more and more. We can consider the inclined wall, inclined backfill, inclined wall, layered soil, and then soil with groundwater table, and then the backfill being cohesive and so on. So if I consider the passive situation, you have the wall which is moving towards the backfill. So it is the wall which is pushing. It is the one, the horizontal force is the one which is causing the major magnitude and which has major magnitude. Therefore, sigma 1 is in the horizontal direction, and sigma 3, which is the weight of the wall, weight of the backfill, will be in the vertical direction. So, in passive earth pressure situation, horizontal pressure is more than the vertical pressure, unlike in the active situation where the vertical pressure is more than the horizontal pressure. So, if you consider any element within the backfill portion, it is subjected to sigma 1 in the horizontal direction, and then sigma 3 in the vertical direction. Sigma 1 in the horizontal direction, sigma 3 in the vertical direction, as you see in the diagram here. So, let us apply the same theory, more coulombs, at the instant of failure. Sigma 1 equal to sigma 3 tan squared alpha plus 2c tan alpha, but for the passive earth pressure case. So, what happens in this case? Sigma 1 is the horizontal stress. That is the passive earth pressure PP. Sigma V is the vertical stress, which is the weight of the backfill. That is simply equal to gamma Z. If you take the first situation when the soil is cohesionless, then C equal to 0. You know that alpha is equal to 45 plus 5 by 2. You have a situation as shown here. Okay, alpha is equal to 45 plus 5 by 2. This is sigma 1, and then sigma 3 is the vertical stress, which is equal to gamma times Z. Then the equation becomes something like this. Sigma 1 is equal to sigma 3 tan squared alpha plus 2c tan alpha. Sigma 1 is PP. Sigma 3 is gamma Z. C is 0. So it becomes PP equal to gamma Z tan squared alpha, or tan squared alpha is equal to Kp, where Kp is the coefficient of passive earth pressure. And that by trigonometric jugglery can be shown as equal to 1 plus sine phi by 1 minus sine phi. So PP is equal to 1 plus sine phi in the numerator, 1 minus sine phi in the denominator, then multiplied by gamma times Z. So PP is equal to Kp times gamma times Z, where Kp is equal to 1 plus sine phi by 1 minus sine phi. So what happens when phi is equal to 0? It is similar to that of a liquid, therefore Kp is equal to 1. On the other hand, when phi is equal to 30 degrees, numerator is 1.1 plus 0.5, 1.5, denominator is 0.5, equal to 3. So Kp is equal to 1 plus sine phi by 1 minus sine phi, okay, will always be equal to or greater than 1. On the other hand, Ka, active earth pressure coefficient, is 1 minus sine phi by 1 plus sine phi, which will always be less than or equal to 1. So this point I want you people to be clear. So now let us try to plot the graph of variation of passive earth pressure. So we know for a cohesionless soil, PP is equal to Kp times gamma z, where Kp is 1 plus sin phi by 1 minus sin phi. When z is 0, Pp is 0. When z is equal to h, Pp is equal to Kp gamma h. And that's why the equation here. And this value is much, much more than Ka times gamma h, because Ka is low, small value, less than 1. Okay. And this is also a triangular load. And hence, the total passive pressure Pp is equal to the area of the triangle, that is half into Kp gamma h into h, half into Kp gamma h square, that is Pp. Where does it act? It acts at a height 1/3 from the height of the base, where h is the height of the wall, or 2/3 from the top apex. Okay, so it acts at h by 3 from the base. And total active earth pressure is simply the area of the triangle, which is equal to half into Kp gamma h squared. Half into Kp gamma h squared. Where is it acting? It is acting at h by 3 from the base. Well, some limitations of Rankine's theory. Wall is never smooth, but we assume it to be smooth. Direction of lateral earth pressure obtained is not correct. So we assume that the lateral earth pressure is always horizontal. But because wall is not smooth, there is always the frictional force which is acting. Therefore, the direction is not normal. And we have not really taken care of cohesion properly. So it's not explicitly considered. In spite of that, this theory is famous because we are likely to arrive at very conservative solutions, and it's very easy to use. The computation is simple. Therefore, we are likely to have, easy solution. Friends, with this brief background, I want to take you on to the numerical problems. We have taken numerical problems from the previous GATE question papers, and also from other sources which are of same standard as that of the GATE questions. So please note, please see, some of the questions are for 1 mark, some of the questions are for 2 marks, depending on the kind of computation which is required. Majority of the cases you have numerical problems. Okay, let me take the first problem. I read the problem here. Consider a rigid retaining wall. Consider a rigid retaining wall with partially submerged cohesionless backfill. Please note, partially submerged, not fully submerged, and a surcharge. So there is a soil, okay, which is not fully submerged, not fully saturated, and on top of that there is a surcharge. Which one of the following diagrams closely represents the Rankine's active earth pressure distribution against this wall? I want you to see all the 4 answers clearly and come out with the right answer. In the first case, you have triangular force. It doesn't take the surcharge into account. In the third case, you have uniform pressure for some distance and then it goes. Okay, it increases. Fourth one also does not look rational. So answer is B. Answer is B because it is trapezoidal. You have the triangular portion plus you have the rectangular portion. Rectangular portion is simply Ka into Q, where Q happens to be the surcharge. Triangular portion has variation ranging from 0 at the top to Ka gamma h at the bottom. So B is the right answer for this. So I want you people to be familiar and hence answer this as clearly as possible. Let me move to the next question. Let me read the question clearly. A retaining wall of height h with smooth vertical back face or back portion, smooth vertical back, supports a backfill inclined at an angle beta with the horizontal. So you have a retaining wall, okay, which has an inclined backfill like this. Inclination angle with respect to horizontal is beta. The backfill consists of cohesionless soils having angle of internal friction phi. So the backfill is a cohesionless soil. So C equal to 0. Phi is the angle of internal friction. If the active lateral thrust acting on the wall is Pa, which one of the following statements is true? And the active thrust, which is acting, total thrust, which is acting, is always parallel to the surface of the backfill. If the backfill surface is horizontal, PA will be horizontal. If it is inclined, PA will be inclined. So let us see the answers. So let me go to answer A is the right answer. Therefore, I'll consider B, C, D and try to prove they're wrong, and we'll go to A. So first one, B says that PA acts at a height h by 2. No, for all triangular loads, it is at a distance h by 3. So it acts at a height h by 2 from the base of the wall and at an angle phi with respect to horizontal. It is not at an angle phi, it is at an angle beta. C says PA acts at a height h by 2. So that itself is wrong. At an angle beta with respect to horizontal, which is correct. Fourth one, D says PA acts at h by 3, correct, but at an angle phi with respect to horizontal, which is incorrect. So very clearly, the correct answer is PA acts at a height h by 3 from the base and at an angle beta with respect to horizontal. So correct answer is A. Okay, friends, let us move over to the next problem. A 6-meter high retaining wall having a smooth vertical back face retains a layered horizontal backfill. Layered horizontal backfill. What do I mean by layered? It is in two layers. Each of the two layers has different soil properties. Top 3-meter thick layer of the backfill is sand having an angle of internal friction phi equal to 30 degrees. And the bottom layer is 3-meter thick clay with cohesion, okay, having C equal to 20 kilopascal. No mention is made about phi, therefore phi in clay is 0, assumed to be 0. Assume unit weight of both sand and clay to be 18 kilonewton per meter cube. Total active earth pressure per unit length of the wall is dash. So please note that the first layer, the top layer, is sand, phi is 30 degrees, gamma is 18, sand therefore cohesion is 0. If you try to plot the earth pressure distribution here, at z is equal to 0, that is at the surface it is 0, it increases linearly and it will become equal to Ka times gamma into 3 meters. And what is Ka? Ka equal to 1 minus sine phi by 1 plus sine phi, which is equal to 0.33. So here the distribution is 0.33 into gamma times 3, 0.33 into 18 times 3. That's equal to 18 kilonewton per meter cube, meter squared. So the point here will be 18 kilonewton per meter squared here. On the other hand, at the bottom you have clay soil. Here it is said phi is equal to 0, same gamma 18 kilonewton per meter cube, C is given. So you have a surcharge. You can take this as surcharge acting on top of clay. You can forget this. You can only consider this as surcharge acting on top of clay equal to Q, which is equal to gamma times Z. That is 18 into 3 meters, 54 kilonewton per meter square. So considering that, I have the equation gamma PA, active earth pressure, is always equal to gamma Z into Ka minus 2C into root of Ka. I repeat, Pa is equal to gamma Z into Ka minus 2C into root of Ka. How did I arrive at this? You know this equation, sigma 1 equal to sigma 3 tan squared alpha plus 2c tan alpha. More Coulomb criteria at the point of on the verge of failure. When you consider the equilibrium at the time of failure, you get this. And active earth pressure case, therefore sigma 1 is gamma z and sigma 3 is Pa. So you get this. For the layer 1, top layer, Ka is 0.33. Why? Because phi is equal to 30 degrees. So 1 minus sine phi by 1 plus sine phi, where phi equal to 30 degrees, you get the value as 1 by 3. On the other hand, Ka for the bottom layer is equal to 1. Why? Phi is 0. Therefore, 1 minus sine 0 by 1 plus sine 0 will give you 1. Now, at point A, earth pressure is 0. Considering the top layer, it is Ka times gamma into H, 18 kilopascal. Considering the bottom layer, I have the surcharge to be considered Ka times Q, that is 1 into Q. Q is the surcharge, that is equal to gamma times Z. Gamma is 18, Z is 354. Okay, 1 into 54, that is 54, minus you have this value. So you need to consider 2C here into Ka is 1, so that is 40, which amounts to 14. So you are deducting this cohesion part, okay, that's going to be the minus 1. So you get this value as 14. When you go to this level at the bottom, C, you have the surcharge weight Ka into Q, 1 into 54, plus you have Ka gamma z into Ka, 1 into gamma z. So z is 3 meters, gamma is 1854, minus 2c into square root of Ka. Ka is 1, therefore 2c, 2 into 40. So 54 plus 54 minus 40, amounting to 68. So these are in kilonewton per meter square. This is the earth pressure diagram. What is the question? The question is that you need to find the total active earth pressure. Therefore, you need to find the area of this earth pressure distribution. So you have the top portion, which is a triangle. Bottom portion, you have a trapezium or a rectangle and a triangle. So find the area of this. And interestingly, you find the area to be 150 kilonewton per meter. And answer is given here. Therefore, the right answer is answer A. So this is how you will be able to solve this problem. And I want you to work numerically. I want you to practice it. So it might take you about 4 to 5 minutes if you know the answer well, or slightly less than 4 to 5 minutes. But you need to remember this equation: Pa equal to gamma z Ka minus 2c to root of Ka. So blindly you remember this. You know Ka is 1 minus sine phi plus 1 by 1 plus sine phi. Substitute the values and arrive at the expression. Friends, let me try to solve a few more problems as much as possible in earth pressure theory. Two different types of soils, soil 1 and soil 2, are used as backfill behind a retaining wall as shown in the figure. Here you see it in the figure. Here gamma T is the unit weight, C dash and phi dash are the effective cohesion and effective angle of shearing resistance. Resultant active earth force per unit length acting on the wall is dash. You need to find the total resultant active earth pressure, the magnitude. So that will be expressed in kilonewton per meter run. You need to find the answer. The values are given. It's a horizontal surface. Soil 1 has the bulk density equal to 15 kilonewton per meter cube. It is cohesionless. Friction angle is 30 degrees. Soil 2 is little more denser. Its bulk density is 20 kilonewton per meter cube, cohesion is 0, and friction angle is 40 degrees. Like last time, remember the major equation for plotting the pressure distribution. PA is equal to gamma z into Ka minus 2c into root of Ka. Gamma z into Ka minus 2c into root of Ka. So in this case, you can find out Ka1 and Ka2. Ka1 for soil 1 at the top, Ka2 is for soil 2 at the bottom. So Ka1 is 1 minus sine 30 by 1 plus sine 30, which is equal to 0.33. Ka2 is 1 minus sine 40 by 1 plus sine 40, which will be lower than for Ka1. The value is 0.217. So interesting point you should know is whenever the friction angle is more, the coefficient of active earth pressure is going to be less. Soil can stand by itself better. Only when soil is very loose, it is going to push a lot of pressure onto the backfill, onto the wall. Okay. So if you make the backfill very dense, possibility of lateral earth pressure being high is less. Keep that in mind. Now, your job is to simply plot the pressure distribution diagram. So, use this equation Pa equal to gamma z Ka minus 2c square root of Ka. So, C is 0, therefore Pa is equal to gamma z Ka. Now, you take the first layer. So, Pa is equal to Ka into gamma z, and 0.33 is Ka. Z is 0, it is 0. And Z is equal to 2 meters. Z is equal to 2 meters. Then Pa is equal to 15 into 2 into 1 by 3, which is equal to 10 kilonewton per meter square. Then when you want to solve for the earth pressure distribution for soil 2, soil 2 is exerted by, an additional surcharge. Surcharge comes from soil 1. What is that surcharge equal to? Gamma times Z. That is 15 into 2, 30. So Q is equal to 15 into 2, 30 kilonewton per meter square. Therefore, you have the earth pressure due to the surcharge. That is Ka2 times. Because we are now into soil 2, Ka2 times. Ka2 is 0.217 into Q. Q is gamma Z, that is 30. So Ka2 is 0.217 into 30, which is equal to 6.51. Plus you have the earth pressure distribution for soil 2. So at this Z will be 0, and you go to the bottom, Z keeps increasing to 2 meters. Correspondingly, you find out that, and the value is found to vary from 0 to 8.68 at the bottom. So earth pressure is 10 here. Earth pressure is 10 in the top surface, and 6.51 is this, and then it varies like this, and the total pressure here will be 6.51 plus 8.68. So what is that you're asked to find out here? You're asked to find out the resultant active earth force. That means the area of the triangle. Area of the active earth pressure. So you consider the top triangle, then the rectangle, and the bottom triangle. Find the area of that. Half into 2 into 10 plus 2 into 6.51 plus half into 2 into 8.68. The answer to is this is 31.7. Therefore, answer is A. Okay, friends, let me take you on to the next problem. A 3-meter high earth retaining wall retains a dry granular backfill. Please note, dry granular backfill with an angle phi equal to 30 degrees, and unit weight is equal to 20 kilonewton per meter cube. If the wall is prevented from yielding, that means there is no movement of the wall. That means there is no strain which is acting. That is, it is at rest condition. The total horizontal thrust on the wall is dash. When I talked about coefficient of earth pressure, I told you two extreme cases. Ka, coefficient of active earth pressure, Kp, coefficient of passive earth pressure. One in the middle is when there is no strain, that is earth pressure at rest. Earth pressure, yes, approximately is considered to be equal to 1 minus sine phi. Remember that. Earth pressure at rest, coefficient of active earth pressure is 1 minus sine phi. So, when you consider coefficient of active earth pressure, coefficient of earth pressure at rest, K naught is 1 minus sine phi, phi equal to 30 degrees, therefore K naught is 0.5, H is 3 meters, gamma is the unit weight 20 kilonewton per meter cube. Substitute and you will find out that the area of the triangle is equal to 45 kilonewtons per meter length. So the answer to the question is C, 45 kilonewton per square meter. Per meter, not square meter. Let me take the next problem. Here you have a clay soil, a rigid smooth retaining wall. Its height is given 7 meters, of height 7 meters, with vertical back, retain saturated clay as the backfill. The saturated unit weight and undrained cohesion of the backfill are 17.2 kilonewton per meter cube and 20 kilopascal. So cohesion is 20 kilonewton per meter square and saturated unit weight is 17.2 kilonewton per meter cube. The difference in the active lateral force on the wall in kilonewton per meter length run up to two decimal places before and after the occurrence of tension crack is dash. So you have to be very careful. You have a cohesive soil which has sufficient amount of cohesion. When there is cohesion at the top, the earth pressure will be negative because of the presence of cohesion. And slowly the cracks start developing. When cracks develop, what will happen? Crack, it develops in the tension zone. And once the cracks are developed, it cannot take any tension further. So that negative, whatever is there, that vanishes. It can only take the positive stress. So before the uh, tension cracks are developed, the earth pressure diagram will be as shown here. And after it is developed, from the zone at z is equal at p equal to 0 till the top, there will be no negative pressure. It will not take any negative pressure. So it has to take only the triangular force. Keeping that in mind, you are again required to find out, Pa is equal to gamma z Ka minus 2c root of Ka. In this case, phi is equal to 0. It is not given, therefore assume that phi is equal to 0, therefore Ka equal to 1. So Pa equal to gamma z minus 2c. When z is 0, that is at the surface, Pa is equal to minus 2c, that is minus 40, because c is equal to 20. When z is equal to 7 meters, gamma z will minus 2c will give you gamma is 20, 17.2, z is 7 meters, c is equal to 20 kilonewton per meter square, and hence you get the value for this one as, let me try to arrive at that new slide. Sorry. pointer often. So, friends, PA, active earth pressure is equal to gamma times Z into Ka minus 2C into root of Ka here. 2C into root of Ka. So, you have the height of the wall as 7 meters. Height of the wall is 7 meters. Then gamma is given as 17.2 kilonewton per meter cube. I don't write the unit here. C is given as 20 kilonewton per meter square. At Z is equal to 0, PA will be equal to minus 40. Okay. And at Z is equal to 7 meters, PA will be equal to gamma, that is 17.2 into 7 minus 40. So you have minus 40 here, and then it extends and extends, goes like this. So this one is minus, this is plus. You can find out what is this depth. That is, you put PA equal to 0, and you have the Z here. So when it is 0, gamma Z is equal to 2C, or Z is equal to 2C by gamma. Z is equal to 2C by gamma. 2C by gamma. This value is minus 40. Then what happens? When the the tension cracks are developed, no longer this tension exists. The earth pressure diagram will become only something like this. So consider this total, and this value, I had just computed this value somewhere. Let me see if I have it with me. I found this value as 80.4. 80.4. So here only 80.4 counts. 2C by gamma works out to be equal to 2.33 meters. And hence, this value is going to be 7 minus 2.33 equal to 4.67. So find the area of the triangle here, find area of the earth pressure diagram, two triangles, this minus this, and only this. The answer to this is 46.6 kilopascal. So any problem, you need to practice a bit and then solve by considering the equation. So this equation you will have to keep by hearted, then only you will be in a position to answer this. So let me move over to the next problem. In the next problem, you have a vertical cut. A vertical cut is to be made in a soil mass having cohesion C, angle of interflexion phi, unit weight gamma. Considering K and Kp as the coefficients of active and passive earth pressures, what is the maximum depth of unsupported excavation? In clay soil, you can have unsupported excavation because of cohesion. So, what is the maximum depth up to which it can stand? So, please note that, let me consider the pointer. Okay. This is the depth to Z naught. What is that? At this point, the pressure is zero. So to arrive at pressure equal to zero, the Z naught is simply equal to to 2C into root of Ka divided by gamma into Ka, or this Ka goes, therefore gamma divided by root of Ka. You should also know that if I put that in the form of Kp, it will be 2C into root of Kp by gamma. So this is minus, and to balance this, you can have on this side the plus portion. So this also will be Z naught. So up to here, the earth pressure will be zero. As long as earth pressure is zero, there is no need for any support. Up to here, total earth pressure will be zero, which is equal to 2 times Z naught. Z naught is equal to 2C root of Kp by gamma. Therefore, 2 times Z naught is equal to 4C root of Kp by gamma. Therefore, the answer is A. Answer to this question is A. So, all other things, are only confusing. You'll have to remove them. So, always remember Ka is equal to root of Kp, 1 by Kp. Kp is equal to 1 by Ka. Root of Ka is equal to 1 by root of Kp, and root of Kp is equal to 1 by root of Ka. That you should remember. So, I have just solved here sigma 1 equal to sigma 3 transport alpha plus 2c tan alpha, where alpha is equal to 45 plus 5 by 2. Okay, therefore gamma z equal to Pa into Kp plus 2c into root of Kp. When Pa is 0, z is equal to 2c by gamma into root of Kp. So z unsupported is 2 times z, that is 4c root of Kp divided by gamma. Friends, let's go to the next problem. A homogeneous gravity retaining wall supporting a cohesionless backfill is shown in the figure. This is the figure. Okay. Lateral active earth pressure at the bottom of the wall is 40 kilopascal. At the bottom of the wall is 40 kilopascal. This one. Cohesionless, therefore, it varies from 0 to 40. Minimum weight of the wall required to prevent it from overturning about the toe. So toe is this point P. Toe is this point P. Is dash. So 40 here, therefore total active earth pressure is equal to half into 40 into 6. Half into 40 into 6 into area of the triangle. Okay, half into 40 into 6. Okay, that is 40 into 6, 240 by 2, that is 120. 120. Where is it acting? At a distance one third from the height. That means 6 meters. Therefore, this is 2 meters. So overturning moment is equal to 120 into 2. So overturning moment is equal to 120 into 2. This moment is resisted by the weight of the gravity wall. So you have the weight of the wall which is acting at the center, assume, and the wall thickness, wall width is 4 meters. So the toe portion here, the restoring moment, Mr, Mr, restoring moment Mr is equal to W into 2. So, assuming a factor of safety of 1, the overturning moment should be equated to restoring moment. So, only unknown here is W. 120 into 2 should be equal to W into 2. So, W weight should be minimum 120 kilonewton per meter run. So, I want you people to consider. Anyway, answer to this is A. Likewise, we can solve a number of problems. Let me read the problem. Surcharge loading required to be placed on the horizontal backfill on a smooth retaining vertical wall so as to completely eliminate tensile crack is. Okay. Here, the tensile crack can develop. This is minus. And I want to eliminate this tensile crack. What can I do? One way is separate out. The other way is, you simply add some pressure on top. What is that pressure you need to apply? That pressure is equal to whatever is the value here to make it zero. So that pressure should be equal to, okay, 2c square root of Ka should be equal to the Q. So, you know that 2c root of Ka, that should be equal to the surcharge pressure. And hence, answer to this question is D. Well, let me read the next problem. A smooth, rigid retaining wall moves as shown in the sketch, causing the backfill material to fade. Please note, how is it moving? This is backfill. So you see the backfill here. This is the backfill. And wall is moving towards backfill. That is, it is passive. Passive earth pressure. The backfill material is homogeneous and obeys isotropic and obeys more Coulomb criteria. Major principal stress. All of us know whenever it is passive case, major principal stress is in the vertical direction. So this is sigma 1. And minor principal stress will be in the other direction, sigma 3. So major principal stress is, first answer is parallel to wall face and acting downwards. It says that parallel to wall face acting downwards. Where is that? This way. No chance. I take the C and D. They are oblique. They are inclined. No. Therefore, the only answer here is B, normal to the wall face. So wall face is like this. It acts perpendicular to the wall face in the normal direction. Well, friends, I think I'm going to stop here. So it's already time is closing up, and we can probably talk a little about Coulomb. I do have 1 or 2 minutes. Okay, he was, his life was from 1736 to 1806, and he gave his theory in 1776. The assumptions made in his theory, I'll be very quickly talking about. Okay, very similar to Rankine's theory. It is more useful in graphical method of solution. Soil is homogeneous, isotropic, elastically undeformable, but breakable, and it is cohesionless. Okay, he also assumed that it is cohesionless. The rupture surface is plane, like before. Failure wedge acts as a rigid body, only causing the translation. When the soil wedge is impending, theory gives two limiting values, active and passive, compatible with equilibrium. So you try to consider the limit equilibrium. Two extreme cases are active and passive. Then the position and direction of the earth thrust are known. You assume that the position as well as the direction of the earth thrust, earth pressure is known. In the wall, if the wall yields and the rupture of the backfill soil takes place, soil wedge is torn off from the rest of the soil mass. It just goes off. Friction is distributed uniformly on the rupture surface. For a rupture plane within the soil mass, as well as between the back of the wall and soil, Newton's friction law is valid. So these are some of the assumptions. Here he also has a few more assumptions. The back face of the wall is plane. Back of the wall is plane. The backfill surface is planar. The surface is planar. It may be inclined or horizontal. Failure is a plane strain problem. Like before, it is a two-dimensional problem extending to great length. So more on this we'll cover in the next class. And till then, goodbye. I want you people to have a go at each of the question, solve them independently by yourself, and see whether my answer and your answers do match. So with this, friends, I'm going to stop here, and well, I'll be meeting again after a couple of days. And thank you very much. I'm going to close at this point of time.
Thank you, sir. That was indeed an informative session which might have enlightened our participant friends on Rankine's and Coulomb's theory in detail and will help to crack the problems in GATE on this regard. So I thank you again on behalf of all the participants, friends. Thank you, sir.
Thank you.
Dear participant friends, kindly join us for our next session at 2 p.m. tomorrow by Dr. N. Bhaskar on engineering mathematics. See you tomorrow. Thank you all.